I'm sorry that this talk is not related to class number. Still, I got the opportunity to talk here. So let's start. So I will talk about multiplicative pattern in synthetic sets. So this work is a joint work with Dr. Bhuvnesh Rao Patil from IIT Roorkee. So first define the synthetic sets. So any subset of natural numbers is called synthetic, L synthetic, if it intersects with every set of L consecutive natural numbers, where L is a positive integer. And we call a set is simply synthetic if it is L synthetic for some L. So in 2006, Bell-Bach and their collaborators, they established the significance for looking geometric progressions, long geometric progressions in synthetic sets. And they established some equivalent criteria for a set having long geometric progressions. And they proposed the following questions, that whether a synthetic set contains long geometric progressions with integer common ratio or not. So in literature, we can see that in a paper of Zemredi that if a set has positive upper natural density, then it contains arbitrary long arithmetic progressions. But such a result is not available in case of geometric progressions. Even there are situations where we can find some sets with positive upper natural density where there is no geometric progression of 3 terms. So such as if we consider the square Ferri numbers, then it does not contain any 3-term geometric progressions. So here we study the synthetic sets and we try to produce some family where we can have some geometric progressions of arbitrary length. So some study was done in this direction, and in 2019, Glasscock and their collaborators, they gave some affirmative answer to these questions, but it was in dynamical system. So they produced some topological spaces, and where they established that this synthetic set, some synthetic set has arbitrary long geometric progressions. So some positive result was there, but as such, it's not clear that whether any synthetic set will contain 3-term geometric progression of integer common ratio. So here the thing integer common ratio is important. So we do not have such clear classification of such synthetic sets which will contain 3-term geometric progressions. So these are some notations which will be used in our results. So for a subset A of n, we define the ratio set by R of A. So this is the set of natural numbers where R can be put in this form. And for a natural subset of natural number and natural number X, we define Tx of A this way. And as usual, D of A defines the upper natural density. So with these notations, what we observe that, first we observe that, so before we state this result, so I will say that even it is difficult to say whether a 2 synthetic set contains 3-term geometric progression with compound integer ratio or not. So we have the observation that if you start with a synthetic set, 2 synthetic set, and if the upper natural density of T of X of A is 0 for some X, then A contains geometric progression of arbitrary length. So this is the first observation. So I will give some hints of this theorem proof. So suppose we have some natural number so that D of Tx of A is 0, then we will produce arbitrary long geometric progressions there. So pick any natural number K. So our aim is to produce a geometric progression of length K plus 1, and it will be valid for any K. So if this is not possible, this means this set A will not contain this type of configuration for any n. So this is nothing but the k+1 length geometric progression. So if A does not contain any, if A does not contain geometric progression of arbitrary length, so this means that this A does not contain this type of configuration for any natural number n. Now, since A is two synthetic, so we use the property of two syntheticity. So if these numbers are not in this set A, then we can say that you just subtract one, then this set is going to be inside the set A, and this happens for all n. So, and this is, if we rewrite this, and we can observe that this is going to be inside Tx of A. Okay, so now for each u from 0 to k, so here we have this condition, and for each u from 0 to k, we define this set. So once we define this set this way, so b of u is nothing but those natural numbers such that this expression lies inside Tx of A. So once we define bu this way, so it's clear that union of all bu is going to be the set of all natural numbers. Now we define a function in the following way. If you define f as a function in this way, then we can see that f of bj is inside Tx of A. Now using some intermediate lemmas and results, we will get some contradiction here. So what we prove that we picked any natural number k, and we proved that that set has geometric progression of length k+1. So thus we find this observation true. So this is our first observation. So anything, there are results in arithmetic progression, many results in arithmetic progressions, but there are only few results in this direction for geometric progression in synthetic sets actually. So the second observation is that if you take any synthetic set A and any two natural numbers, that if you can find some natural number x so that Tx of A is not synthetic. So it's important if we can find some such x such that Tx of A is not synthetic, then we have some observation that either x is in that ratio set or this quantity is in the ratio set of A. So once we can prove this, we have two corollaries, immediate corollaries, that if you start with a two synthetic set and you can find some u, it's in this case it's a natural number, u coming from the set of natural numbers, so that u of A is not synthetic, then we guarantee that A contains this type of configuration, and it happens for all natural number k. So why we are interested in this type of results? Because even in two-term geometric progression, we are unable to prove whether any two synthetic set contains three-term geometric progression or not. So recently, in a few papers, there are only few results about two synthetic sets and three-term geometric progressions. So these results may help to produce such family actually. So this is why we are interested in such type of configuration. And the second corollary is, we have to note that here the same, under same assumption, but Tu of A is not synthetic for some u, and u is coming from A. Here the condition is u is coming from any natural number, set of natural number, and here particularly u is coming from the set A. So in this case, we can say something more, that A will contain this type of configuration. So this gives some idea how to get three-term geometry progression there. So even if it's not clear, that when we are unable to give some clear classification when two synthetic set will contain the 3-term geometric progression. But in our next results, hopefully we will be able to produce some criteria on 2 synthetic sets using these results. And our final results, it will show that when a ratio set of a synthetic set will contain infinitely many terms of an arithmetic progression. And this results is based on some properties of IP sets. So what do you mean by an IP set? So for a subset of a natural number is said to be IP set if we can find some sequence of natural numbers so that this set fs of this sequence is defined in this way, just finite sum taken over from all the elements of the sequence. If this lie inside A, then we set the set A to be IP set. And two properties we will use in our proof, that you pick any x from the set of natural number and you take xn, it will intersect every IP sets. And the second one is the Hidman's result, that if you partition any IP set, so you partition the IP set A into finite number of parts, then one of the parts is going to be IP set again. So this is Hidman's result. And with this, we have the following lemma, that you take any sequence in natural number and any integer. Here A is integer, not a natural number, it's any integer. So you define B in this way, then pick any element from the set B and take any integer k, then we can produce some integer t such that, positive integer t, such that st is inside B and t is of the form t equal to 1 mod ks. So once we have this, so with little effort, we can show that if we start with a synthetic set A and you pick any natural number k, then the ratio set will contain infinitely many elements of the form this. So this is the final result of our paper. So this is all. And so I just quote the results of our paper. We haven't included any detail. So these are the references. So that's all.